Hello, I am physicist Leslie Ruby Garcia Bernal, currently pursuing a Master in Industrial Physics Engineering, and I will be presenting my poster titled Enhancement of Optical Properties of Cadmium Sulfide's Colloidal Quantum Dots by preparing a core shell system of cadmium sulfide, zinc sulfide. In this work, I report some results from the synthesis of core shell system of cadmium sulfide and zinc sulfide quantum dots. The synthesis to form the quantum dots was done using a method called one-pot, and microwave irradiation was used as a thermal treatment to activate luminescence. Additionally, I conducted optical and structural characterization to also evaluate the efficiency of this chemical treatment process at different concentrations and at different times and temperatures of thermal treatments. Quantum dots are nanostructures made of semiconductor materials that can be synthesized through various methods. The most attractive feature of these nanocrystals is the luminescence they emit, which can vary across different ranges depending on the bandgap energy of the semiconductor material being used. In this case, cadmium sulfide has a bandgap of 2.42 electron volts, meaning that the luminescence obtained can cover the entire visible spectrum, from red to violet, corresponding to the largest to smallest nanoparticle size, respectively. However, since it is a material with multiple surface defects, achieving good luminescence is difficult. Nonetheless, it's possible to use chemical treatment on cadmium sulfide quantum dots to create a core shell system, where coating with another material, in this case zinc sulfide, can passivate the surface and improve the optical properties. Furthermore, being able to manipulate the surface and optical properties in a quantum dot synthesized in an aqueous solution allows for potential application in various fields, such as biomedical applications. For the synthesis, a stock solution was first prepared using cadmium sulfide and urea as precursors in a 4:2 ratio, along with trisodium citrate and a stabilizing agent, which in this case was trimercaptopropyonic acid. They were added one by one to deionized water, using magnetic stirring to mix, allowing 1 minute for mixing between each reagent. Finally, the pH was adjusted. This stock solution allows liquids to be taken for the direct heating or for an additional chemical treatment, which is mentioned in step 2. A 16 milliliters portion of the stock solution was taken and placed under magnetic stirring to add each of the precursors, which in this case were 2. These were previously dissolved in 2 milliliters of water to be added one by one. The result solution is 20 milliliters, allowing it to be used in a reactor for thermal treatment by microwave irradiation. The machine used was an Anton Par monowave 300, and the temperature varied between 100 degrees Celsius and 130 Celsius. The results obtained are as follows. In figure 1, part of the test performed can be observed. On the left is the base, corresponding to the cadmium sulfide quantum dots, which have poor luminescence and a very faint reddish-brown color. The following results corresponding to chemical treatment by adding a zinc sulfide shell, resulting in a change in luminescence and emission colors. A blue color was even obtained by size separations. In figure 2, some of the characterization studies performed on some samples can be seen. In UV-Vis spectroscopy, the baseline is shown in black, corresponding to cadmium sulfide quantum dots, where absorbance peaks are not apparent, unlike in the other samples where they are more definite at different wavelengths, particularly in sense M1, M4, and M13. In photoluminescence, the difference between the samples is significant. The base is at the bottom, and the best one, M4, has the definite peak. It is noteworthy that this is the sample with the highest concentration of shell precursors. Although this peak is still somewhat broad, the emission is becoming more defined with better properties after applying chemical treatment. For X-ray refraction, the base and M3 samples were used. When viewed under UVB light, M3 was one of the best samples. We can see that, compared to the base sample, there are few variations in the crystallographic planes and difference in peak yield. One of the things we can consider is the variation in nanoparticle size, as well as a chemical difference and internal tension and deformation in the crystal structures. In the case of higher angles, we correspond to this. Compressive stress can cause the diffraction peaks to shift. In conclusion, using chemical treatment provided improvements in the optical and structural properties of the samples. Not only do we achieve a higher luminescence, but the quality of the emission has been maintained over time compared to cadmium sulfide quantum dots, which have shown a decrease in luminescence. Higher shell concentration resulting in better photoluminescence outcomes. However, it's important to consider the amount of reagents used to avoid oversaturation. With these results, it's confirmed that the formation of this core shell system allows for more efficient quantum dots, and this structure can be considered for potential application in fields such as medicine. This is my reference and acknowledgements. Laboratorio de Nanociencias y Nanotecnologías, la Universidad Autónoma de Nuevo León, for the use of the infrastructure and technical support for X-ray diffraction characterization, and Dr. José Quiñones Galván by his technical support for photoluminescence characterization. Thank you.